All right, let us make a start for today. So how is everyone doing? Bad? Like super bad? Just medium bad? Medium, okay, not bad. All right, so 2 more weeks, 2 more lectures. Basically, hopefully by the end of today, we will have all the kind of groundwork that we need in order to do the important theorems next week, which are the ones that really will help you understand Maxwell's equations. So we're trotting along quite nicely. The thing that you will have noticed with this course is that each week builds on the previous weeks. So although our final exam will only notionally, explicitly cover material from weeks 4, 5, and 6, you can't just forget everything from weeks 1, 2, and 3, because then you won't be able to do anything in weeks 4, 5, and 6. So I would recommend just keeping revising, in particular just getting comfortable with our double and triple integrals, because they're going to come up quite a lot. Any questions, queries, complaints? Awesome. Okay, so my aim is to have the midterms graded by the beginning of next week at the latest. Yeah.
I'm sorry, do we have a quiz for week 4?
Yes, but not yet. I haven't put it up yet. I just want to see how far we get today. Yeah. So I will put it up later today. Yeah. And I will give you appropriately long extra time. I mean, I think what I will say is any quizzes from now will just be due by the end of the course, so that you can just, because I know you've got like bunches of stuff to do, so you can just time manage as best you can.
Also, let us by the end of the course. Everything by the end of the...
Yeah. Okay, so remember for this course, any extension will be granted except for the midterm. But because I just want you to do the work and do it thoroughly. But in order to be guaranteed a resit, you need to have done all the work. So you need to have submitted all the quizzes, you need to have submitted all the tutorial assessments, just so long as you do that before the end of the course. Yeah? Yeah.
The quiz for week 4 is like for the previous week, right? So it doesn't depend on this material, right? Or we don't have quiz for week 4?
So I think what I'm going to do is put together, because we've got 2 more quizzes to do. So I will put together the quiz from the next quiz will cover what wasn't covered in the previous quiz, plus what we do this week.
Mm-hmm.
And then the final quiz will cover what we will cover next week.
So there will be one quiz for 2 weeks, right?
Yes, because we only have 5 quizzes. Yeah. Okay, but I will tell you what the quiz is covering. Yeah. All right. Okay, so what are we looking at today? So you might well have forgotten about vector and scalar fields because we had the midterm, which might have blotted that out. So we're going to just do a little bit of recap on what those are and talk about a specific kind of vector field that comes up a lot, which is called a conservative field. Then we're going to trundle into a new kind of integral. Yay! Because we haven't seen enough. These are called line integrals. And then we're going to use the idea of line integrals and combine it with the idea of vector fields to have line integrals of vector fields. But because one kind of new integral in a lecture is not enough, we're also going to look at surfaces and surface integrals. Luckily, these are really just kind of a 2-dimensional analog of line integrals. So a lot of what we've done over here, we can just kind of use, except trundle into 2 dimensions instead of 1. And then if we are lucky, we'll talk a little bit about this, but I'm not sure that we'll get there. Okay. So, just to remind you, so far, we started out by looking at vector-valued functions. So this was a function where you put in a scalar and you got out a vector. So we were thinking about things like, for example, seeing where something is at a particular time. So if you wanted to talk about position or over time, velocity over time, those are the kinds of things we were describing. Then in chapter 13, we looked at scalar-valued functions of a vector. So this was where we put in, for example, a position and got out, for example, a temperature. And now what we're looking at over here is we're looking at a situation where we put in a vector and we get out a vector. So for example, you're thinking about the gravitational force at a particular point, you put in the position, and what you get out is the gravitational force. Both of these things are vectors, the position and the force. That's what we want to be able to do. And as we said, physics has so much in the way of vector fields. That's why we need to study them. To remind you the way we visualize things, because obviously visualizing something that takes in 3 numbers and puts out 3 numbers is going to be very hard to draw. But we sketch these by taking our 3 space and then at each point kind of putting where the little vector points, and that's about the best that we can do. We show these vector fields by usually breaking it up into components. Here we're in Cartesian components, I, j, and k, but we could be in a different coordinate system. And each component, as its coefficient, has a function of x, y, and z, which spits out a number. So each component of these is what's called a scalar field, and these are the things that we studied previously. Okay. And if we're in 2 dimensions, this is the kind of thing that we get. And you can start to see where all your pictures of magnetic fields and things come from. And we talked a little bit about why we love vector fields, but the one that is going to really occupy us today is that we notice that we've actually encountered a vector field before when we took the gradient of a scalar field. Because remember, when you take the gradient of something of x, y, z, you get out a vector. So we have already encountered vector fields, and there's a close link between scalar fields and vector fields, and the link is this gradient thing. Okay, and then we had a quick look at an example. For example, the gravitational field of a point mass, and in 2 dimensions looks something like this, which is kind of what you'd expect. Here's your mass, and you want to know how much gravity is it exerting. Well, closer to the mass, there's going to be a bigger force, further away, smaller force. Okay, and that's just the 2D version, but you can imagine what the kind of 3D thing would look like. And we also talked a little bit about field lines. So this is where we basically draw a line that would mark where, if this, you were thinking of this as a fluid, for example, where the velocity at each point is given by the arrow, then if you put a little ball bobbing in the fluid over here, the field line marks out kind of where it would move. And for interest, I talked a little bit about how you can sometimes get the field lines from the vector field, but we're not worrying about that too much. This was all for interest. Okay, so as I said, we don't have to express our vector field in Cartesian coordinates. We could just as well do it in polar coordinates, for example. So let's just have a look at what this kind of thing looks like. So here we're just thinking about in 2 dimensions, just so we can draw things a bit. But you could do it in spherical coordinates if you're in 3D. All right. So suppose we've got a vector field, and we want to express it in terms of a unit vector in the r direction. So let's think about what this looks like. So our unit vector in the r direction is always going to be pointing out from the origin, but it's going to point in different directions depending on which theta we've got. So here's our little r hat. And if we think about, perhaps, let me make this a little... Okay, so let's think about having our particle at, or thinking about point position r over there. So this is big R. What are the unit vectors doing there? Well, our little r hat points outwards, like so. And our theta hat says which is the direction that theta goes in. Well, theta increases in that direction. So we've got theta hat like so. Okay? Making sense? So we can express, but we can also combine get our r and our theta from our I and our j hat. You can check this. It's our usual. Here's There's theta, there's r, there's y, there's x. And if you want to express our little r hat, then it needs to be basically it's x plus y suitably scaled. And that's given by cosine theta, which is your x component if r is equal to 1, and sine theta gives you your y component, assuming that r is equal to 1, which it is because it's a unit vector. Yes? Yep. And similarly, you can look at theta hat and you can figure out, you get theta hat like so. Okay. Things to point out. So this is your kind of conversion factor. If you're given, for example, a field that's in Cartesian in I, j, and k, or in I and j, you want to convert it into r and theta, that's your conversion. You always need to know both directions. The point over here is, how do we know that theta hat is just r rotated? Well, we know that dr by d theta, as you change the angle, r changes in that direction. Dr by d theta tells you which direction r is going to change in. So theta hat is r rotated by 90 degrees, wherever r happens to be. Okay, and we're using f sub r and f sub theta just to make it clear when we talk about our components up there that the component has already been converted into r. It's not f1, which was the component with respect to x. Yeah, it's getting messy, I'm sorry. And those are labels, not derivatives. I don't know. Okay, I don't know a better way to do it. And when we're in our polar coordinates, then we call f sub r the radial component, the component heading out from the origin, and theta is called the transverse component because it's at right angles to the radial component. Okay, so what do we get if we try to sketch the field lines for this simple vector field given by the field that says go 1 in the radial direction and 1 in the theta direction at each point? Oh. Okay, so let's have a look. So let's have some axes.
Yeah, something like a soft spiral.
Okay, so I'm hearing something like a spiral.
Yeah. Because
How do you figure?
Whereas if you look at any given point.
yes, but then you probably have one vector here. The function is given by the sum of the components theta and the r. So it's going to be pointing in the direction of the sum, and
Yep.
then you're going to get a circle
Exactly.
for every given radius.
Okay, so let's plot a few points just to see what's happening. Okay, so let's have a look at this point over here. So what do we get? Our field there, so our little r hat, always points outwards from the origin. So there's our r hat. And our theta hat always points at right angles to that in an anti-clockwise direction. So our little theta hat must be doing that. There's our little theta hat. And so we're adding these together to get the component of our f. So if we've got that plus that, then there's my f at that particular point. Yeah? Okay, and we can keep doing that, but it will be much clearer if I show you over here that we end up with this kind of thing here. Yeah?
Sorry, I don't get how you figured out that R is like that and theta is like that.
So R, because of how they're defined. So R always points in the radial direction, which goes from the origin to your point. So, for example, if I was over here, my R would point like that. Okay? And then once you've got R, your theta hat is always kind of 90 degrees in an anti-clockwise direction from there, So for example, here, my theta hat will look like that. So this is the kind of the weird thing about polar coordinates that takes a little while to get used to. We're used to an x, y, and z. We know x is there. Sorry, well, if we're doing it in 3 directions, there's x, there's y, that's z. They never change. They're always in the same directions. But here, our unit vectors depend on where you are in the plane, or the 3 space if we were in spherical. Okay, yeah?
In this case, what was the 1, 1 that you mentioned at the beginning? These two here.
The 1, 1?
You said that we need to go 1 in the r direction and 1 in the theta direction?
Because hidden over here is a 1 and a 1.
Yeah, but I mean like in the graph that you mentioned, what is the 1 and where is the 1, 1? Is that the length of the vector?
Yeah, because they're unit vectors. Okay, so if we were to just, so let's put this one over here, and this one over here, and you can start to see how this would build up into a picture pretty much like this. Okay, so spend some time just plotting some of these little vectors for yourself. Try and do them sort of accurately so that you get, you'll start to build up this picture. And then if we draw the field lines, so we, for example, we start here and we were to just follow this vector and keep going and following vectors, I'd end up doing something like that. Cool. Okay. And you can see from this sketch over here why it would be useful to be using polar coordinates here. You would not want to have to try and describe this bunny in x and y. It would be a pain. And you could imagine you would have horrible coefficients to your x hat and your y hat, whereas here our coefficients are 1, and life is delightful. So you kind of shifted the pain to trying to understand what the hell is going on here, and plotting these. But in terms of calculations, much, much simpler if you're in polar coordinates here. Right? Okay. All right, conservative fields. So this links back to the thing I underlined in why we love vector fields. So we've said that, so we know that the gradient of a scalar function is a vector field. So one of the things you might ask is, can you go the other direction? If I hand you a vector field, could you always find a scalar field whose gradient is that vector field? I mean, why not ask it? So the thing we're asking is, if I give you a vector field, can you find a scalar field such that, in fact, I can write my vector field as the gradient of that scalar field? And the sad answer is, in general, no. Very generally. But it turns out that there are actually a lot of common vector fields that we use for which you can find a scalar field. And if it turns out that we can find a scalar field whose gradient gives us our vector field, then we say that f is conservative. And we call the scalar field the scalar potential. Yeah.
Is this why, for example, we talk about potential energy? Okay.
Exactly.
Now a lot of stuff starts to make sense
Yep.
in physics too.
Yep. So when you're talking about potentials, which are scalars, they are coming from a vector field. And that's the link. And this is kind of one of the powerful things. So a lot of the vector fields that we use in physics are conservative. So they come from a scalar potential. And that means essentially that you can work with the scalar potential, which is much more straightforward than working with these crazy, like, multi-dimensional vector fields. Okay, so we need to look at that. So what we're saying is that if our vector field is conservative, then we can write it as its components as just the partial derivatives of our scalar field.
Can you remind what scalar field is?
So a scalar field is something where we put in an x, y, and a z, and we get out a single number. Yeah? And so those at least were reasonably straightforward. We could kind of draw them and kind of work with them and think about them. Yeah. Okay, so why do we care? Well, as I've just said, scalar fields are really quite a lot more straightforward to work with and to kind of understand. So that's always good. So let's just have a look at how we can, so we'd like to know, okay, how do we tell if something is a conservative vector field? So I'm going to look at example 3. I'm going to talk about equipotential curves a little later. So for now, we're just going to see if our vector field is conservative. And if it is, find a potential function, and then describe the field lines. Okay. So one of the ways to see if something is conservative is just say, well, can I find a scalar field that works? If I can, then it is. If I can't, there's no guarantee that I didn't just screw up. So you can't say, well, I couldn't find one, so it isn't. But if we do find one, then it is. Okay, so what do we need for it to be what do we need? Well, to be conservative, we need to have that the x component, so f1, not the derivative here, is equal to d phi by dx for some phi. This is the phi we would like. Okay? And we also need that our y component, so let me move this over a little bit. So in terms of the specific example we're looking at, our x component is just x, and our y component is minus y. So we need to have that d phi by dx is equal to x for this magical phi that we're going to try and find. And then we also need that if we take the partial of this magical phi with respect to y, then it's going to be equal to our f2, which is minus y. Okay. And I'm going to take a little bit more space over here. So let's just have a look at this first equation over here. Can you tell me a function who, if I take the x derivative, will give me an x? X squared, okay. Oops. Yes. Is that the only function?
Plus c.
Okay, and is it plus a constant c, or could I go even more complicated?
I could add everything in y.
Okay, so any function that looks like an x squared over 2 plus some function of y will work. So let's just put in a general kind of case, and I'm going to put plus some g of y. Okay, because remember, when you differentiate with respect to x, y gets treated as a constant. And we can play the same game and say, okay, well, what does the phi need to look like if its partial derivative gives me a minus y? Well, it's going to need to be minus y squared over 2, and then again plus some, in this case, function of x. So if I can find a phi which meets both these criteria, then we've found our phi, or a phi. Well, if I think about my g of y as being y squared over 2, and I think of my h of x as being x squared over 2, then essentially this function, let me write it down, works. Because our phi is equal to x squared over 2 plus some function of y, but it's also equal to minus y squared over 2 plus some function of x. Yay, okay, turns out our vector field was conservative. Who knew? And I've kept this very general, so in fact we have an entire field of, or an entire family of phi's for all the different constants that you could possibly have. For any constant there, the potential will work. Okay? And we want to describe the field lines. So this would be a good opportunity for you to practice sketching some field lines by just drawing some little vectors. But, well, let's draw a couple. Okay, so we're thinking about what vectors. So I think at this point it's easier actually to look at the function. I mean, to look at our vector field. So this is, what did I say? Okay, let's just draw a couple. So if I'm looking at this point over here, say 1, 1, so x is equal to 0, and I'm in the minus y direction, so I'm going to be something like that. If I plot any of these here, if I'm over here at minus 1, then I'm going to be doing something like that. I'm going to be doing something like that. Something like that. You can plot some more points over here. So let's assume that this is 1, 1. So then I've got a component in the, so that's minus 1 in the x direction, and down here, so I'm kind of doing something like that. Okay, you can kind of see how these go.
Yeah.
Yep. So we end up with field lines that do something like this. Okay, so you can check those. Okay, so please add to your daily regime of sketching graphs, sketching field lines. Okay, so the thing to kind of notice here is that we don't have a clear-cut test for is it conservative or not. The first thing to try is can we find a scalar field? So what happens if something isn't conservative? So let's try the same trick. So now we want to show that this velocity field is not conservative if big omega is not equal to naught. So what does it look like if we can't find it? Well, we play the same trick. So here we have, that's our f1, so that's equal to minus omega y. And here's our f2 is equal to omega x. And we know that we need to have that d phi by dx is equal to minus omega y, and d phi by dy is equal to omega x. Okay, well, let's try the integrating trick that we just did. So what would I need to differentiate with respect to x in order to end up with minus omega y? Sorry?
Minus omega y squared divided by 2.
No, be careful. I'm differentiating with respect to x.
Oh, it is just minus y omega yx
Exactly. Plus,
plus something.
okay, so I'd have minus omega y x plus some function of y. Yes? All right, and the same trick again with our partial with respect to y. So what do I have to differentiate with respect to y in order to get this? Omega xy. Okay. Okay, and now see the problem that we've got over here. we have two terms that have x and y, but this one is minus omega xy, and this one is positive. And there's no way that we can combine these two kind of requirements into a single potential that works unless our omega is equal to 0, so that these two terms don't feature. So there we go. So let me make a note here. So these two terms are never equal when omega is not equal to 0. And since those two can never be equal, we can't have our phi that includes them, because it has to meet both those criteria in order to be a valid phi. In which case we would have that our phi would be some constant, because our phi needs to look like this, and we've said that our omega is going to be 0, so our phi needs to look like a g of y, but it will also need to look like an h of x, which means it can't have x's or y's in it, because again we're going to have a problem with one of them. So the only solution that we have is that we have a constant scalar field. Okay, so that's kind of what it looks like when things go wrong. Yeah.
So the question is, F1 is the derivative with respect of x?
No.
No.
No, so that's the thing that I said that's annoying here. Here we're using F1 to say this is the x component of
Okay,
f.
I didn't understand that.
I know, and I'm sorry.
Can you please explain this again, why it's constant again?
Okay, so are you happy? So we're trying to find some phi which meets that criterion and that criterion. Okay, so we can't have a phi that has an omega that's more than 0, because then it would have to have both minus omega yx and omega yx. And I mean, if you put those both together, they'd cancel. Okay, so we can't have either of those terms. So we're left with saying, okay, well maybe, so what our phi has to have is either, it needs to consist of just a function of y, but it also needs to consist of just a function of x. So supposing we picked, I don't know, x squared. That would be fine for this one, but then over here, we've said that omega needs to be just a function of y, so we can't have any x's in it. And this one says it needs to be a function of x, we can't have any y's in it. So the only thing that we're left with is that it just has to be a constant.
And if we would have a rule that omega couldn't be 0, in this case, would it be a scalar potential function or not?
Right, we can't find a function that meets both these criteria for omega not 0. Yeah, we can't find one. Yes.
Just to be clear, omega yx is not partial derivatives notation, right? In the second.
So this is omega times x times y.
Oh, okay, I was saying something. Okay, sorry.
So,
I know, it's just mad.
Okay.
so
Yeah.
if we take omega to be 0, it is conservative, and because we have a specific value for the scalar potential, we have a constant, and that's it.
Right, so if we take omega equal to 0, then it is conservative. But I mean, that's not very interesting, because then it's just our velocity field's not doing anything. Our velocity field says, I'm dead still. But, you know, that's fair. I know how it feels. Okay.
So this is the requirement. So if we cannot find a scalar potential, it cannot be conservative.
Exactly. Because what it means to be conservative is that you have this. Yep. Okay. So notice that this bit over here, well, actually, let me just show you what we want. So based on what we just did, there is a way that you can do a quick check to see how likely it is. But notice that this is a necessary condition, so it's not sufficient. Okay, so if our vector field is conservative, then it is the case that this is true. But the reverse doesn't apply. So it's not the case that if this is true, then f is conservative. So you can't just do this and say, yes, it's conservative. But you can check your f, see if this is true. If this is not true, then you're definitely not conservative. Okay, so it's kind of it's a pre-check. Okay, so if I hand you something and I say, is it conservative? You can do this check. If the check fails, then you can say it's not conservative. But if the check succeeds, then it's not conclusive. You have to go and find the wretched thing to prove that it is. Okay. But sometimes it's just a useful quick check. Okay, so I briefly mentioned equipotential surfaces and curves earlier and said we'd come back to them. This is us coming back to them. So you've probably, if you've been doing any physics, talked about equipotential curves, places where, for example, lines of force are where the force is the same or the electrical potential is the same. These are the things that we're thinking about. So we have the idea of the equipotential surface. These are the level surfaces of your potential function. So we're just using different language to talk about level curves or level surfaces. That's all we're doing. And we know from the work that we did on level curves and level surfaces that they are orthogonal to the surface that you're dealing with. So they're orthogonal trajectories of the field lines. So they intersect our field lines at right angles. So if we have a look at the function that we just did a little bit earlier, so we found our field lines, those that we sketched, and our equipotential curves are always at right angles. So our equipotential are the green things that look like that. And you get those from solving this thing, which is our potential, setting it equal to various constants k in real numbers. So it's literally just finding level curves or level surfaces. And the reason why you might want to do this is if, for example, if this was, for example, an electrical potential or something like that, things along here all have the same potential. Things along here all have the same potential. So that's kind of heading into your physics intuition as you need it. Okay. So a couple of quick examples of vector fields that crop up a lot. So you can read through this discussion here. It's really just the idea of a point source. So you could think about it as, for example, if you have a fluid that is being produced just at a single point, so increasing amounts of fluid coming out, so it's a point source. Or if you're thinking about, for example, an electron with its little magnetic field or electric field or whatever you want to think about, these are point sources. What do they look like? Well, we've already seen them. They do things like this. Radially out like this, and usually decreasing. Okay, things like that. And your equipotential surfaces will be either circles or spheres, depending on the number of dimensions. Nothing particularly exciting here. Similarly, a sink is a negative source, so it's got the same look except everything's pointing in. So imagine that, for example, you have a fluid and you have a tiny little drain, and everything's draining out at that particular point. Okay, so we have our point things like this. And again, equipotential surfaces are circles or spheres. And then one that you probably recognize, we also have, what does a dipole look like? Dipole looks something like that. So if you go on and study electrodynamics, you'll be working with these potentials a lot. So just kind of want you to have a feel for where they came from. All right, brief pause. Any questions? Okay, so the thing to take out of everything that we've done so far is this idea that ideally we would not like to work with vector fields because they are complicated things. It would be very nice if we could instead work with scalar fields that we've been doing so far. And it turns out that if your vector field is conservative, then you can find a scalar field that is equivalent to it. How do you do that? Well, you just try and find it. We have a brief test to check if something is definitely not conservative, but we don't have a definitive test for is it conservative, other than finding the scalar field. Okay, so you need to do some practice around finding scalar potentials for vector fields or explaining that they're not conservative. Okay. All right, new kind of integral. So, way back when you did calculus 1 and you were wanting to find integrals, what you were doing was you wanted to find the area under a curve, essentially. And it was a curve that lived in flat space, so this is what you were doing. But obviously what you'd also like to be able to do is suppose that you have a curve wending its way in 3 dimensions. We'd still like to be able to find the area under that curve. We would, really. Okay, so this is what we're doing. We're moving from just thinking about finding kind of like a little flat area in 2 dimensions to thinking about, well, what if this thing was kind of like curvy in 3 space? We would still perhaps like to find that area. That's what we're building up now. And these things are called line integrals. So it's the area of a curved surface. Whoops, that was not what I expected. Okay. So how do we go about this? So let's just do a brief recap when we were parameterizing curves. So you might also want to go back to the notes on parametrization because that's coming up now. We're going to be doing a lot of that. So when we were talking about arc length, we said that the length of some curve, so we're just looking in 2 dimensions here. If you want to find the length of this curve over here, we showed that it's equal to, well, I parameterized this curve as some r of some parameter t for naught is less than t is less than or equal to b. Okay, so I have some parameter t, and at t is equal to a, I start over here, and as I move t, I move along this curve over here until t gets to b, where I end up there. And if I've done that, then I can work out the length of this curve by doing this crazy integral over here. And we did do a little derivation of that. Hopefully it's not too obscure. So essentially what we need to do is we need to find the derivative of our parameterized curve and then integrate with respect to t. And we did that because we're not really clear on kind of integrating in many dimensions, but we know how to integrate over a single variable. So it's quite nice to go from this slightly confusing thing to this clear, straightforward integral over t, even though it looks a little hairy. Okay, so we can actually quite straightforwardly figure out our line integral. It's going to look very much like what we just saw up there, except now we're just integrating the function that we're interested in over that curve. So nothing very much has changed. We're still integrating from a to b, so we've got the same parameterization, and we're integrating over the curve, but now we want to integrate the function value. So the picture that you want to have in your head over here, here is our curve C that we've originally been talking about. We want the area under this blue curve, our f, along curve C. So if you were to kind of think about it in the calculus picture, what you'd want is your little ds times the height of the curve. But our ds is given by, as we said over here, our ds is given by dr dt by dt. Kind of make sense? Okay. the moral of the story is there's not a lot new here. We're just now suddenly able to integrate yet more things. So really, we've already seen line integrals. We just didn't call them that. But this was just the line integral which gave us the length of the particular line. Now we're integrating other functions along that line. Okay. So let's just do an example. Okay, so we want to evaluate this integral, so x squared plus y squared, along the curve C, where the curve C is the straight line from the origin to point 2, 1. Okay, so let's just think about what it is that we're doing here. So this red thing is our surface x squared plus y squared. Let's just leave that for a moment. Okay, so that's the red thing. And our straight line from the origin to the point 2, 1 is this thing here. So that's our curve C. So that's not an E, it's a curly C. Okay, and what we want to do is we want to work out what is this area here. That's what we're trying to figure out there. Yeah? Okay. So at this point we go, okay, I think we just had a formula for that. Let's go and have a look. So here's our formula. Actually, I'm just going to do... Okay. Okay, so we want to convert this into this thing over here. So you'll notice that one of the first things that we need is we need to parameterize our curve. Because this bit over here says this is a parameterization of C in terms of T. So we're going to need a parameterization of the curve which goes from the origin to the point 2, 1. Okay, so let's work out that parameterization. Pictures always help. So we want to go from the origin to the point 2, 1. Okay, so all right. So a parameterization, I need to have an x of t and a y of t, so that when t is equal to my starting, so let's say maybe from 0, I start here, and then when t is equal to the final value, I end up there, and at each point in between, I move along this line. Any suggestions?
Y x equal t, y equal 1 half.
Sure.
Is it?
So I'm going to take a slightly more straightforward one because fractions scare me.
Yeah, it's probably. Yeah, you can use it.
Okay, I'm gonna do this. I'm gonna say.
T, yeah, that's what we wanted to. Yeah.
Okay.
Yeah, that was what I was thinking.
Yeah.
Actually.
Okay, let's check that this works. Okay, when t is equal to 0, I'm over here. When t is equal to 1, I'm over here. So that seems good. And anywhere in between, I'm a linear combination of that. So it seems okay. And that's reasonable. Okay, so my r is equal to 2t in the I hat plus t in the j hat. Okay. And I need dr by dt. So I take component-wise derivative, so I've got a 2i plus j. All good? And let's go back to what do I need? And I need my f parameterized. So basically my f, which over here is x squared plus y squared, I now need to convert each of those x's and y's into something involving t. So we know that x, so let me just remind you, this is x of t all squared plus y of t all squared. And so that's going to be 4t squared plus t squared. Yep. So putting it all together, the weird so here's the original thing in terms of the particular curve, but we didn't really have sensible limits. But now we've converted this into an integral with respect to t, and our t limits are given over here, 0 to 1, of, let me put 5t squared I think. Did I? Wait, no. No, I forgot. Bad. Yep. Okay, so I need the modulus of this. Is root 5. So putting it all together, because I need, can I just copy this? Let's see all the things that I need. I need f of r, which in this case is 5t squared. I need the modulus of dr, so that's a root 5. And I need a dt. Yeah?
Where does the 0, 1 come from?
So the 0, 1, because I'm integrating with respect to t, and my limits of t for my parameterization are 0 to 1.
How do you choose them in the parameterization to be 0 and 1?
Because that was what worked. I mean, you choose the parameterization. So we created a parameterization that worked. Okay, we did bunches of worksheets, go revise. Okay. Well, let's finish this up. So this is going to be root 5 times 5 times the integral from 0 to 1 of t squared. So we're going to get a half times the integral of t squared from 0 to 1, which is just 1, and we're done.
Over three.
All right, what did I forget?
Over 3. Because you have
Oh,
t
3,
and
sorry.
squared.
Over
3 times.
3, there we go. Better?
Yeah.
Okay. Okay, let's just talk through briefly everything that went into doing this. Okay, so what we're trying to do is find the area under this surface where the base of the area we're trying to find is given by this curve here. So we're wanting to find this yellow area here. And because we did a whole bunch of work before, we have an equation over here which tells us how to do it. So this is notionally the area, but in practice, who the hell knows how to do that? We don't. Let's convert it into something that we do know. So this version says if we parameterize this curve with respect to a single parameter, we can change that integral into this thing, which is just a function of one variable. So in order to do that, we need a parameterization of the curve. Now, any parameterization that is valid will do. So we picked one that seemed to make sense. So we picked this, but you practiced a whole bunch. And in fact, we could do a different one. So if we'd taken, for example, we could have gone, t goes from 0 to 2, and we could have had x is equal to t and y is equal to t over 2. That would also have worked. Then our integral would have had slightly different limits, but we'd get the same answer. Once we've got our parameterization, we can work out our position vector. So this is our curve, but parameterized. And we worked out the derivative, and we found this factor here. We converted our function, which was originally in x's and y's, into a function of our parameter, put it all together into an integral that now was just dependent on t. Integrated, and that's what we got. All right. So for this kind of problem, almost the hardest work is going to be finding the parameterization. But the good news is there's not just one correct answer. So if, for example, so I'm not going to go through this except to show you. So we're thinking about a circle of radius a with a center of the origin in the xy plane. So here's our picture. That's terrible. Okay. And suppose you were asked to calculate, so you don't need to know about moments. This is just to show you, but the moment is the tendency to rotate about a given axis. So here we're asked to find what is the tendency of something like this shape to rotate around the x-axis. But you don't need to know the details. What you need to know is that the thing you want to calculate is this integral of y with respect to ds. Okay, so this is the kind of integral that we're dealing with. And so you would need to parameterize. Well, you could parameterize the curve using that parameterization there. And you can work through just to check that you can do the algebra. And you get 2a squared. But you could equally well use a very different parameterization. So over here we used minus a sine t as my I component. Here we're using x. And here we're using a minus x squared. So quite a different parameterization using x as opposed to using t. But if you do the work and you can handle all the roots, then you'll get the same answer. So the key thing is not to find the correct parameterization. The key is finding a straightforward parameterization that works for you. Yeah? Okay.
Just a question. The moment is tau, right? Or no?
Not quite.
Okay, never mind.
Yeah. And just to reiterate, you don't need to know what moment is. I wouldn't ask you this in a test or exam. I just wanted to show you an example where they have two quite different parameterizations that get you the same answer. Okay. All right. All right, you don't have to know about moments. Okay. Okay, pausing for a moment. Questions? Okay, so 5-minute break. But please be back within 5 minutes. All right.